Welcome back. This is Jürgen with his patent, the configurable ontology to data model transformation COT. With COT, we transform industry standard ontologies like the FIBO in-house ontologies into data models, and we can reverse engineer our existing enterprise models into RDF-OWL. And here we have an overview of the COT patent with its resources and requirements. The FIBO is the authoritative model of financial industry concepts, their definitions and relations. The EDM Council is the global association of more than 100 financial institutions, and it teaches data management best practices and develops data standards. Now, one of these standards is the FIBO. EDMC members, in other words, banks, developed the financial industry business ontology, FIBO, as a business conceptual model. And in its latest version, it has more than 2,300 classes that detail financial products, services, business entities, and processes. The financial industry business data model, FIBDM, derived from the FIBO. And more than 3,500 users have downloaded the open source version of the data model. The COT, the configurable ontology to data model transformation, is the technology that created the FIBO data model. And the United States Patent and Trademark Office, the USPTO, has issued a patent for COT. Well, during patent search and examination, I had to study half a dozen patents, and I found it very challenging to understand them. And that is due to the very exacting nature of drawings and the specification text. So this practical COT patent overview is for ontologists and data architects. And here we look at the patent purpose and structures, the distracting USPTO format, and the user-friendly COT patent resources. And also we discuss how COT exceeds the USPTO requirements and what makes it a very strong patent. Patentability. So as per United States Code, a US patent grants the owner the exclusive right to prevent others from making, using, selling, or importing the invention. If the invention is a process, this right also extends to products made using that process. In other words, it extends to FIBDM. And to be issued, a patent according to USPTO must meet 4 conditions. Utility, so it must be practical, not just a mere idea or theory. It must be non-obvious, not a true invention, and not just tweaking or improving something that already exists. It should be novel, meaning not described before. And here the examiner searches for so-called prior art in patents, academic papers, and other publications. And finally, its description must be clear, following the exact USPTO requirement. Now, a patent is structured in 3 parts: the claims, drawings, and the specification. Now, the exclusive rights only pertain to the claims. If it's not claimed, it's not protected. And the software invention is typically claimed to be a computer system, a storage medium, and a method. And the drawings illustrate the claims. So, for example, here's a figure 2 is a UML system diagram showing the key claim terms: configuration, extraction, transformation, and load as components. And the specification explains the drawings. So a section in the detailed specification explains the diagram objects and their connectors, like how they work together. Yeah, and when the USPT says clear description, it means a very exacting format. So here we are on the USPTO website, the detailed description. As we can see, every paragraph has to start with a number. And then we have all these numerals within the text. They actually refer to the same label in the drawing. And if we look at Google Patterns, which has a slightly better rendition, we can see the drawings. First, they're all in black and white. Then again, they have these numerals, and some are upside down and so on. So it is necessary, certainly, for an unequivocal communication between examiner and patent applicant, as well as in patent litigation. However, it makes it really hard for computer engineers to read a patent. Yeah, so the patent resources are meant to supplement the official publication on USPTO and Google Patents. No, and at the bottom of the page you find links to the specification, claims, and drawings. So if we look at the patent specification, well, you will see that first of all, it doesn't have the numerals in the text, and you can see here actually the figures are embedded, just like we would do on a design document. And also next one here, if we look at the drawings, now here's a gallery of all the drawings that you can print and and if you click on a drawing here, a screenshot of the metadata set, you get it in high resolution and in color. And the latest here would be if we look at the claims. So here claims page has an introduction, and now let's look at the system claim here. And what you see here, right to the paragraph in the claim, you see a link. No? So F stands for figure. If we click on this, it takes us right into the patent specification. And likewise, if we click on the paragraph, it takes it over there. And finally, if we click on a T stands for table, it will take us to the table in the patent specification. Yeah, so let's go over the patentability requirements. First was utility. No? It has to be practical and useful. And well, here, I guess 3,500 users who downloaded FIPDM attest to that. No? They find an ontology-derived data model that preserves the complete RDF-OWL semantics and annotation properties useful. And the success of FIPDM is due to its quality compared to rudimentary ontology to data model transformations. And what I asked myself at the time was, how would I, as a data architect, design a perfect data model based on the industry standard? And the answer is like in the FIPDM diagrams. No? Like this, I would do it. Entity names based on the naming standard, associative entities, not mere relationships derived from object properties, and resolving the very complex RDF-OWL semantics, no? Like class restrictions and inverse properties. Yeah, so utility, the background section in the specification details that. No? And here the manual of patent examination and procedure says that it should first describe the field of the invention and then provide a description of related art. So the COD background explains model-driven engineering, data modeling tools, and the importance of data modeling transformation. Now, giving an example that we all know, like we transform LDMs to physical data models. And the specification acknowledges that some data modeling tools like Spark.ca or IBM LDA provide an import of RDF-OWL files and subsequent transformation. And it also points out to their shortcomings. No? And shortcomings, in other words, these are our requirements for FibDM and COT. So they don't enable the user to change the mapping and transformation rules. And in particular, we cannot apply a naming standards. In other words, it's a press one button and no configuration. And per default, in these tools, object properties transform into data model relationship, and this is wrong. No, because it loses metadata for particular design patterns, no, like hierarchies of object properties, no. And if you want to look at this closer, you can see my article. Ontology object properties are data model associative entities, not relationships. And also traditional transformation pass ontology files. They encounter elements of the ontology and create elements in the data modeling tools as they process the source files. Now the parsing approach reaches its limit with very large ontologies like the FIBO. Now the FIBO has 250 RDF-OWL files. No? And then frankly, when I tried it, some of the tools just crashed on me. Yeah, so an invention must be non-obvious and novel. And here basically the parsing approach has reached its limit. And I think it cannot be tweaked or improved to produce anything like the FIBO data model. And now the solution to the problem is a radically different approach. So COT uses SPARQL to extract ontology metadata from an ontology platform, in other words, an RDF store. It transforms ontology metadata into standardized metadata sets, and that gives us a holistic view of the ontology. In other words, I have one metadata set that shows me all the classes, all the object properties. And then I can deal with challenges like duplicate names or inverse properties. And also COT works in set operations rather than procedural algorithms. No? And so in other words, it's a 4GL language, ETL language. And that, of course, is much clearer and descriptive than procedural coding. So metadata sets require that we configure settings for our transformation rules and provide overrides. And in reverse, a fully configurable transformation needs a metadata set. It does not work file by file parsing. Yeah, about the claim structure. So in most software patterns, the method is the central important claim, no? Which well, makes sense intuitively. No? So the method, that's the process, no? Or the algorithm. And then the other claim types, no? Like the system merely implements the method and the medium stores the computer code. Now in COT, the metadata sets are the central innovation. So hence the medium claims are most important. And this comes from because the COT approach is basically ETL, extract, transform, and load. And that reflects here as table 1 of the specification shows here in the components. No? So we have different components, different Excel workbooks for extraction, transformation, and load. And then it reflects in the metadata sets for ontology, generic, ER, and then the specific data modeling tools. and they are all implemented in the first embodiment as separate Excel workbooks. Well, summary and conclusion. We looked at the FIBO data model, the transformation ontology, the United States Patent and Trademark Office requirements, and we looked at the FIPDM patent resources, which make it easier to read and understand the patent. And finally, we took a look at the COT claims for system, method, and medium. And of course, here, if you like to read in more detail, look at COT.NET patent, and then, of course, consider licensing the patent's rights and the COT application. Thanks for watching.